Well, good afternoon. My name is Juan Trujillo. Along with me are my team members, Michael Suarez and Frank Calao. We're the second FSAE team, and we will be presenting on the chassis, suspension, drivetrain, and also the ergonomic system of the vehicle. So a little bit of the background in terms of what we do. We are forced to research, design, validate, test, and eventually compete. And a lot of the things that we're doing right now is the research and design sector of it. So we build off on previous year's teams, what they've done, as well as other teams and what they've done, and we try to build up on these different scenarios. So some of the things that we'll be working on, as you can see in the background, is going to be the chassis. So we're going to reposition the pickup points on the suspension to try to maximize the efficiency of it. We're also going to do the chassis, or redesign the chassis to not only the specifications of the new rule parameters, but also to be able to move these suspension pickup points. And we're also going to be tackling the drivetrain in terms of being able to remove the wear and tear that the current differential has on the vehicle. So some of the motivations that we have, as the previous team mentioned, we obviously want to score higher as a school. Aside from that, we want to be able to take what we learned in the class and apply it to the real world, and we want to be able to learn how to manufacture and apply complex components into the race vehicle. So in terms of the drivetrain, we're going to be specifically looking into differential. So differential is a limited slip differential, and it's composed of a planetary sun gear assembly inside of a housing. So right now, one of the problems that we're having is that because the housing is of a different material than the gears, the housing is wearing out. So our task is to be able to make sure that either through the implementation of similar materials or of sleeves or some type of design, we're able to reduce the wear inside of the differential and increase the life of it.
So for the chassis, as mentioned from the previous team before, every 2 years there's a cycle where we need to redesign the actual chassis. Since time constraint was very short with us as far as gathering all the actual components of the vehicle together and assembled in December, we were working hand in hand with the actual rule book and guidance of the actual SAE rules and regulations. So our choice was for the wide range of different types of frames, which we have monocog, carbon fiber, we have aluminum material, and we also have chrome alloy steel. The choice of the frame that we chose was tubular space frame. Reason for this was because for triangulation, it offers a more structural rigidity for the actual frame. And proper triangulation is very important because when passing inspection, all of these are very crucial and very important for the team to adhere to so that we don't fail technical inspection. As well with the chassis, very important is the actual ergonomics of the vehicle, which has to deal with the packaging and constraint of the actual seating position. Previous years, we've had very slouched positions, so a change to the actual seating position was made as increasing the seat panel so that we have a more upright position and more comfortable position for the driver. These templates, as you can see towards the right, are templates that we use when designing the actual frame within SolidWorks. The template all the way towards the bottom is used to make sure that we pass technical inspection, as well as the 95th percentile male, which we call person.
So a little bit about the suspension. Basically, we all know that the suspension needs to take in the loads of external loads, the load of the driver, and also the weight of the frame, and it's all the other components. So basically using tire data, taking into account vibrations and adding dampeners and springs, and then with the basic components also would have to be we're using control arms, uprights, hubs, and then the main focus of the suspension is camber adjustment and toe in and toe out. Basically, it's the perpendicular angle that the tire does with the surface of the street, and then also we have belt cranks and push rods and pull rods.
So for the actual designing of overall chassis, what we did is from previous years we had the resources of the CAD designs for the previous chassis. So what we started off was reverse engineering as far as getting the full chassis designed in SolidWorks and running the simulations for deflection and stress analysis. It's very imperative that the actual frame of the vehicle is safe. So the SAE rule books adhere to us for testing side impact, frontal impact, and rollover impact. Since the first design alternative that we chose passed all of the deflection parameters, which is the front, side, and frontal impact, all of the deflections have to be with under 25 millimeters. Some of the design options that we chose was opening the rear box. Reason by doing this is because the differential as it sits now has a chain clearance problem. So we opened up the rear box so that we can better adhere to the chain clearance. And when we did all our deflection analysis, both alternatives passed technical inspection, but there were failure points as far as in the front portion of the actual design. So this is why we chose design alternative 2. We used reinforcement bars along the side of the impact, along the side of the frame. This next analysis that we did was the stress analysis. Since all deflection for both alternatives passed, we later went into the stress analysis and saw that with the frontal impact, we had a failure of the actual material. When we added the support structures towards the side, we were well under the actual failure criteria that we needed to do.
So, for the suspension, we use a software called V-Suspension, and then, so basically this software, you adhere to all the frame, you add the frame dimensions, and you play around with the uprights, the upper control arms, the lower control arms. And what the purpose is to move the roll center, which is what causes the body roll of the vehicle, move the roll center very close to the center of gravity. So our roll center was below ground, and after all the iterations, we got that the roll center went up to approximately 1.457 inches from the floor. So it adds to less body roll. And then as shown here on the side. So we also tackled camber here, and basically the left and right tire camber is negative 1.587 degrees, and that's just mainly because we try to focus so that the roll angle is less, not past 2.2, but less than 2.2. So we got a roll angle of 1.9 degrees.
So in terms of the organizational, right now we have finished up most of the design for the chassis, and then what we will be tackling through the summer is finalizing the design of the suspension, also looking into the alternatives for the drivetrain and the actual manufacturing of the chassis. So one of the differences that we're thinking about this year is actually rather than bending and notching the tubing ourselves, we're going to have those done by local companies. And the finalized chassis should be done by the end of the summer or beginning of the fall semester. In terms of global design, we actually work with 2 schools, one in Canada and one in Venezuela. And what we do is we change different criterias between all 3 schools. And one of the reasons why we do that is to get a different perspective as to how other countries are tackling problems. As well as exchanging information to make sure that we try to get the best overall design. Some of the standards that we use are ASME, SAE International, ASTM, and Formula SAE. The most crucial one is the Formula SAE rulebook, which is very strict, specifically when it comes to the chassis design. And we would like to open up the floor for any questions you may have.
I've seen chassis for a while, and the question I ask first is, why did you go so flat on this chassis design? And the reason I ask it, I'm looking at 2 places on the design that have 6 welds coming together in a single place. To me, that's a pretty hard thing to do.
So, well, as mentioned before, since time constraint was one of the things that we had to adhere to, we reverse engineered the previous chassis from before. So since that passed technical inspection and we were able to compete with that actual frame, we went based off that frame, and then we fixed the things that we needed to fix that were recommended from the judges. So chain clearance from the actual differential was one, and another was actual validation for the suspension. So instead of, how would you say, going with the actual suspension that we had from before, we wanted to validate that. That's the reason why we use the suspension software like V-Suspension, and the actual points at which the welds, as you see right there, the 6 tubes that meet at one point, one of the criteria for the actual rule book is that each node for the suspension point has to at least have 3 bars connecting to that point. And the triangulation.
3 bars is not 6 bars.
I agree with that. That's a good validation point. And the reason why we ended up going with that was because to connect those suspension points to the rest of our chassis, we needed these extra links in order to.
So let me understand. Your suspension will be connected at the 6 bar link.
Yes. So as you see through this figure right here, our suspension pickup points in the front are going to be within these 4 nodes, and then respectfully towards the back, connecting the 4 suspension points towards the rear box. So the reason why there's so many links at the front suspension point, at the front of the vehicle, is since we had a lot of problem with the frontal impact in our simulations, we needed these triangulations to strengthen the rigidity of our chassis.
Another point in terms of.
My worry is that one set of heat effect zones are going to impact another one, and having that many welds in one location would be a concern to me. Whereas if you put some kind of a structure, maybe a plate or something in there that you could connect to, that then was what you connected the chassis to, maybe it would be a stronger design. That's my concern.
So in terms of the rules, particularly for the opening where the driver's legs are, there can't be great openings. So you have to close off those sections with one of 2 options. You can either have the space tube frame design, or you can have a carbon fiber monocoque. And we don't believe the team as a whole can manufacture the monocoque right now. So that's why we also have to take into consideration that they have a mold where that template you cannot have holes bigger than that template within the frame for the safety of the driver.
One thing also to add, this is, as so far it is now a prototype, there's still a lot of data to get from the suspension. And once we get that data, then we know that we can remove some bars, we can add more bars. We have to add more bars, we remove them. All that has to do with also with the suspension, so we still in that phase.
Okay, great, thank you.
So, I noticed you guys picked chrome alloy steel. What type of chrome alloy steel?
Well, we go based off the actual, like we mentioned before, a lot of the actual decisions were based off of what is allowed through the rule books. So the specific chrome alloy steel, I don't have the exact detailed description of which actual steel we're using, but it's going to go hand in hand of what is allowed through the actual rule book.
Because you guys did simulations.
Yes.
So in other words, the tensile strength for all of the different types of alloy steel are different.
Yes.
That's why it's important to know what you're actually using. So for our follow-up question for that, what kind of simulations have you guys already performed?
We performed the simulations of side impact, frontal impact, and rollover simulations through SolidWorks.
So in other words, stress bearing simulations.
Excuse me?
Stress-induced simulations.
Yes, stress and deflection.
And you guys haven't done any factor of safety simulations? That's very important too.
So the factor of safety was done with the stress, and we were adhering to the yield strength of the actual material. So if our stress was surpassing the yield strength, then we were failing, and that's what was occurring with the first alternative. So we added structural supports on the side of the vehicle to adhere to these failure points. And then when we reran the simulations, we saw that our stress values were much lower than the actual yield strength, so then we weren't failing at that point.
And your bars are pretty much hollow bars, correct?
Yes, they are.
Are you putting that correctly in your simulations?
Yes,
Hollow
so
bars.
I'm glad you mentioned that because I forgot to mention it earlier. Through the actual rule books, we have 3 types of wall thicknesses that we're allowed to use within the frame, and they're all sectioned. As you can see, the actual frame is different colors. So the blue, red, and gray are different wall thicknesses. The colors are to depict the different wall thicknesses. The largest wall thickness is, of course, going to be where our main support is, which is the main roll hoop and the steering roll hoop. And then following that would be the red bars, and then after that is the gray bars. And the wall thicknesses are .095 for the blue, .065 for the red, and then .047. All of them are in inches for wall thickness.
So since you guys are doing a lot of simulations and it comes to the with circular objects, what kind of mesh size are you using? Because
So
the
we
mesh
use
sizes
various
can actually impact you.
various ranges of mesh sizes. At first, we were using as fine as possible. We were acquiring problems getting a full mesh for the actual frame. So there's particular points within the frame where we use even more finer meshes in the actual certain spots where the actual software can't get the entirety of the mesh. But we use fine, as fine as we can, so that we get the best accurate results.
And also like a comment, like I told the last team, I'm also telling you guys, you know, especially since the last team kind of depends on you guys to be done with your work at a timely manner. Time is important, still research.
Yes.
Thank you.
Thank you.